In the spirit of the tutorial today, I want to give you an overview of denoising and how it has contributed to various different areas of work that I've been involved in. I myself have worked on denoising and super resolution for many, many years, and it's really gratifying to see it kind of come full circle and its usefulness become as clear to everybody as it has been to me and a few of my colleagues for many years. So the first thing I will do is give you a sense of how we can use denoisers as a kind of engine for a natural image decomposition. I'll talk very generally about the structure of denoisers. I'll talk about denoisers as the engine of denoising diffusion models. You may have heard a lot about them recently. They're a very, very hot and popular topic in machine learning. And then I'll talk about denoisers as implicit regularizers. So that's kind of the 4 chapters of the talk, if you like. All right, so let me talk about first, what do I mean by denoising? It should be obvious to everyone here, but I'll say it again. It's sort of the simplest of inverse problems, if you like. You've got a clean signal, it's corrupted by noise, and you'd like to remove it. What we're going to do is to create a filter, some kind of function that you push the image through, and what comes out is hopefully as close to the clean signal as we possibly can get. Denoising has come a long way. It's produced really impressive results on device. You know, any mobile phone that you use, whether it's an iPhone or Pixel or Samsung or whatever it is, has this as one of the very core features that you're using every day, every time you take a picture. And it's quite amazing what you can do. You can denoise a typical size of an image coming out of a mobile phone is about 12 megapixels now. You can, in a few hundred milliseconds on a device, you can get near state-of-the-art quality. So it's kind of amazing if you think about what you can do. There's a long history of development here, and I'll just kind of step through a few of them. You know, with the start of sort of the space program and so on, there was a lot of early work done in this area. A bunch of heuristics were developed for spatially adaptive filtering. Robust statistics were brought into the picture. PDE methods were introduced, anisotropic diffusion, Beltrami, total variation. Some of those heuristics were fortified a little bit in things like the bilateral filter. Of course, the wavelet revolution happened in the 90s. Self-similarity, things like BM3D, which dominated kind of the high-quality denoising for a number of years. Empirical bays were introduced, and then finally sparsity had a lot of contributions, things like KSVD, et cetera. And so this got to a point where around 2010, one of my students and I, we looked across the literature and we noticed pretty much every paper that was coming up with results was coming to performance in terms of quality. It was very, very close to every other paper. And so we asked ourselves this question, is denoising dead? Like, are we done? Have we solved the problem? Is it finished? And we reviewed many, many papers, looked at some kind of fundamental performance bounds that you could do by doing statistical analysis. And we discovered that there was still some room to improve. But really, the bigger thing that happened was that not just us, but many others discovered that you could do many other things with denoisers, that just getting rid of noise in images in and of itself wasn't the end goal, that you could expand the range of things you could do. But of course, there was still a lot of work to be done. And over the next 10 years or so, many, many new methods were developed, most of them having to do with machine learning. And in fact, the state-of-the-art methods nowadays are no longer things like BM3D, they are neural networks. Okay, so to kind of close out this summary, again, let's think about general not linear denoisers. These are filters, you can think of it as a function that maps the interval 0 to 1 crossed with itself n times, n being the number of pixels, to the same interval. This turns out to be kind of important. You know, the images don't have arbitrary values, right? You know, you have 0 to 255, you know, if you have an 8-bit image, or you want to normalize the 0 to 1, so keep that in mind. You can think of them typically as sort of nonlinear low-pass filters, right? They're getting rid of some random high frequencies and keeping everything else hopefully intact. All right, so let me talk about a very natural way of using denoisers to do just very general image processing. So think about it the following way. Suppose you have a denoiser that you like, it performs well, and you can apply it to an image that's this f of x that you see here. You can write x as a decomposition of the denoiser applied to it, the smoother, plus what's left over. What's left over we call the residual. As you'll see later, I'll call it also a Laplacian. That'll become clear in the proper context. But now I can take f of x and do the same thing to it. I can take f of x and think of it as an image, and I can apply f to it again and look at the residual of that, and it's still a perfect decomposition. And I can continue this process as many times as I like. This actually works pretty well, and it's kind of well defined if f is non-expansive. You can imagine if f is expansive, if you apply f multiple times, you just get things blowing up, right? So that's one condition that we generally like in denoisers. Okay, but now let me take f and parameterize it with a few parameters. These could be the weights if the denoiser is a neural network. It could be the weights. It could be the denoising strength, or any number of other things. And I repeat the same thing. So this equation that you see down here, x is decomposed into a first piece, which is the filter applied n times, and then an accumulation of the residuals, okay? And the residuals are just the difference between applying f k times and k plus 1 times. That's it. All right, now that I have this, this is what I call the decomposition, right? I've taken a signal x and I've broken it down into this very, very simple decomposition. Now, what I'm going to do is take these pieces and recompose them back together, but not in an identical fashion as how I started. Namely, what I'm going to do is to put, let's see, is there a laser pointer here? I guess not. Okay, so I'm going to put them together, but with some coefficients in front. So I put some betas here, and I put the betas here, and I compute the sum. And now what you have on the right-hand side isn't the same image x, but you have some changed version of x, right? This is what we do in image processing. We take an image and we produce a different version of that image. And so now I have alpha and beta as my control knobs. Now I can define, if I have pairwise examples, let's say I have an input image and an output image that is different in some fashion. I have a bunch of examples of that. I can learn the parameters alpha and beta, and I can define a loss function that has a training error and a regularization part that regularizes the parameters. And I can have an entire system for doing image processing just based on a core denoiser engine. So this is kind of how it works. You start with an input. You're basically breaking the input down into a base layer and a bunch of details. One thing that you see here that's different is I'm also putting the filtered versions through a nonlinearity. And that seems a little weird because I didn't use that nonlinearity when I decomposed the image. But remember, whenever we compute an output of a filter, we always normalize it to the range 0 to 1 anyway, because for display purposes, we need to do that. So this is a very natural way of doing that. So that nonlinearity ends up showing up in kind of machine learning for very different reasons, but we use it here to basically make sure that everything is normalized. So you can take an image and do various nice things to it. So for instance, you can have this picture, and now you don't just need to do denoising. You can reduce wrinkles, or you can create a cartoon, or many, many other things. You can take an image and squish the dynamic range so that you get a nicer looking output. You can do dehazing. These are all done by changing the parameters and learning different things from reference data. Okay, so this is meant to just give a very simple intuition of what you can do with denoisers. So now let me move on to talking about the structure of general denoisers. Okay, so first let me go through some nomenclature. Many of you will probably be familiar with these. And so I'm just going to try to put them in some categories. The first group of filters that I want to talk about are called pseudo-linear. You all know what linear filters are, right? The only difference between pseudo-linear and linear filters is that take a linear filter and imagine the coefficients of the linear filter depend on the input. Okay, that's a pseudo-linear filter. And many filters that have become super popular over the years, things like non-local means, bilateral, BM3D, et cetera, fall into this category. Then, of course, there's sort of the standard Bayesian approaches like maximum a posteriori, minimum mean squared error. I'll talk a little bit about those in a few minutes. And then there are other types of approaches like PDE-based methods or neural network approaches. All right, so let me talk about pseudo-linear denoisers first. As I said, it's just like linear filters. You know, you have the input pixels get added with some weights and they point to an output pixel, but let's imagine those input pixels affecting the weights that you're using. It's convenient to write this in matrix form. So I'm just taking that equation that I wrote up there, and I am stacking all the weights that point to a particular output pixel into a vector. And now I stack those rows into a matrix, and now I have this matrix W. And so now I can write the filter as f of x equals W times x, except that W depends on the data. And what does that W look like? When the filter depends on the pixels, what does it look like? Well, here's one example. These are weights that are computed using non-local means. So xi and xj, imagine these are pixel values at two separate locations, or two patches centered at two separate locations, I and j. And so you compute these weights k between every pair, where you fix one and you compute the difference between every pair. And so this is what they would look like. So all the weights computed for all the pixels in the image as compared to the blue pixel would be the thing on the left, and respectively for the thing on the right. The difference between K and W is that W is just a normalized version of K, where the rows are normalized to sum to 1. That's it. These are really attractive, and part of the reason they're attractive is that they are basically two stages. There's a nonlinear stage where you compute the weights, and once you've computed the weights are fixed, and then it's a linear filter. You apply it, okay? It turns out you can also show that many of the filters that are constructed this way are in fact approximations of Bayes denoisers. We've written this up in a number of different papers, not just us, but many other folks. So these are basically empirical Bayes estimators that try to approximate the minimum mean squared error. Just for reference, also keep in mind, I'm going to call x minus W applied to x as the residual or the Laplacian, again, as I mentioned before. All right, now let's talk about map versus minimum mean squared error. So this is, you know, right out of statistical signal processing. Of course, I used to teach many years ago, so close to my heart, and I'm sure to the heart of many of those in the audience here. So a map denoiser, you're taking the posterior, and you're looking at the peak of the posterior. Minimum mean squared error is not looking at the peak, but it's looking at the mean or the expected value of the posterior. And they don't coincide, obviously. They would coincide if the distribution P of u given x was perfectly symmetric, or if the variance of that posterior distribution was really small, then it would be really close to each other. But they don't coincide in general. It turns out they do have many interesting things in common, though, which I want to draw. So if you look at map denoisers, you have this structure where the first term, norm of u minus x normalized by the 2 sigma squared, that's basically as a result of assuming the noise is Gaussian and zero mean. And then the second term is negative log of the prior that you're placing on the image. It turns out this form, which is very familiar to us as a very simple kind of description of a maximum posterior denoiser, in the optimization community, it's also known as a proximal operator. And in particular, when phi is convex. So one of the things that happens is that it turns out because of this, proximal operators have these really nice properties, one of which is that you can write them in this particular form. So the map estimate can be written as x minus sigma squared times the gradient, not of phi of x, but of phi sigma. And what sigma is the standard deviation of the noise So phi sigma is a kind of smooth version of phi that you started off with. And let me show you a graphical example of this. So suppose that phi is L1, and that's the regularizer. It turns out phi sub sigma is the Huber loss. It behaves quadratically near the origin, and it behaves linearly outside the range here, -1 to 1. And now if you compute this x minus sigma squared gradient of phi sigma, what you get is precisely the soft thresholding operator that perhaps many of you are familiar with. All right, what about MMSE? MMSE is a very different kind of beast in the sense that it's oftentimes much more complicated to compute. Is a rather nasty integral on the right-hand side that is sort of frightening to compute oftentimes. But there is a bit of magic that gets rediscovered over and over again in many different communities, something called Tweedy's formula. Tweedy's formula, as you would look at the integral, you would imagine, okay, I need access to P of u given x in order to compute that integral. Tweedy's formula says, no, you don't really need P of u explicitly at all. What you need is you can simply get away with knowing P of x. Okay, so you don't need the prior, you just need the blurred version of the prior, which is P of x. And the way it works out, that right-hand side is equal to x plus sigma squared gradient of P divided by P. Now, you can rewrite that a little bit. Remember that gradient of P divided by P is just gradient of log of P, okay? And I can rewrite things by just changing the notation a little bit. And again, I have a very similar form, which is x minus sigma squared gradient of phi sigma x, except that I put a little tilde on top of it here. This is also a smooth version of phi, but it's not the same smooth version that you saw for map. It's a different smooth version in the sense that this is basically using the blurred prior to define phi sigma tilde. But broadly speaking, the form is basically the same. And so here's another graphical example of that. Again, you start with L1. The phi sigma tilde also looks like a smooth version. This is no longer just behaving quadratically at the origin and linearly. It's something different. It's actually a somewhat nasty closed form. And then if you compute this difference, again, you get something that looks like soft thresholding, but I call it smooth thresholding because the middle part is no longer flat at 0. It's got the smooth transition. Okay, so let me summarize what I've said so far. Pseudo-linear denoisers, you can write them as W of x times x, or you can think of them as x minus Laplacian applied to x. Map estimates, x minus sigma squared gradient of phi sigma, which is a Moreau smooth loss. And the minimum mean squared error, basically the same form. The point I'm trying to get across is that all of these denoisers have a very particular form. It's like x minus something. And that something, if you think about it, essentially a perturbation of identity. Imagine a situation, what happens when noise goes to 0? What is the ideal behavior of a denoiser when noise goes to 0? It should be identity, right? It should just give you the image back. So as soon as you add noise, you should be departing from identity. So you think of denoisers, certainly for small amounts of noise, as perturbations of identity. They're obviously shrinkage operators, and you're taking x and you're pulling something away from it. You can also think of it as a gradient step on some energy function, right? So x minus sigma squared small, and that's the gradient step, right? And so what I'm getting at is that you can think of this even more broadly than these three frameworks that I just described. In particular, you can think about describing denoisers in terms of energy functions. So let's write this very general form where V is just some vector field. And that vector field may be defined as a gradient of some energy function. And in fact, you can train that energy function. You can associate a cost or a particular value to different versions of an image and to different images. And if you do that, then you can write f of x as the gradient of what's inside the brackets, which is a quadratic minus e of x. Okay. This has various advantages that for technical reasons turn out to be really important later on. There's a nice paper that describes this approach, by the way, as well. If you describe them this way, what you get is that, first of all, because F can be described as a gradient of a scalar field, F will be, by definition, a conservative vector field. And this turns out to be technically a useful and important thing. Also, what it means is that the Jacobian of F will be symmetric by definition. That's another technically useful thing. And I remind you that both MAP and MMSE also satisfy this property, which is something that often goes unnoticed, but is technically very, very important. One thing I didn't mention is these nice properties that I just talked about. Can you say that for these pseudo-linear denoisers as well? Can they be expressed in terms of some energy function? It turns out they can, but under some provisos. If W of X is symmetric and it is scale invariant, meaning that if you multiply W of X, you multiply X by some constant, it gets pulled out, then you can write F of X in terms of this energy function where E is in fact X transpose W of X, X. So this is like a quadratic form, but you can think of it as a sort of pseudo quadratic form where the matrix, the positive definite matrix in the middle actually depends on X as well. Okay, so what are we to take away from this up to this point? Well, if you can describe a denoiser as X minus the gradient of some energy function, I'm going to parameterize this description with a T, which is, if you think about it, you can think of it as a variance of noise or some kind of scale parameter. I can write this because it's basically exactly the same form as you saw before, for instance, for the MMSE. I can also turn this equation around, and I can write the gradient of the energy function as X minus F of X, which is the residual divided by T. So the right-hand side, you've got a scaled version of the residual, and on the left-hand side, you've got this energy function that, if you like, somehow describes a metric on this manifold on which these images live. And the gradient of that is like a tangent space, right? So what it says is that the residual of a denoiser is telling you something about the local geometry of some presumed manifold on which images live. To put it more intuitively, what it says is that if you have a good denoiser, it allows you to understand something about the geometry of the space and allows you to sample from that space or to project onto this manifold. And I put project quotes around project because I know the audience that I'm talking to is not strictly speaking a projection. It just gets you a little bit closer to that manifold when you take this step. And again, there's many, many papers written on this topic as well. All right, so this leads me to talking about denoisers as engines of diffusion models. So denoising diffusion probabilistic models. I'm curious to hear from you, the show of hands, how many people have heard of diffusion models? Okay, so many, okay, most of you. This is a super hot topic. To be honest with you, it's kind of hard to keep up what's going on. There's something like probably dozens of papers every week published on this. One of the things I personally struggle with is try to understand what is exactly going on, like what is the structure and how do I understand what's going on and the variety of different approaches that are being taken. So we've worked with one of my colleagues, Mauricio Del Bracio, to try to understand these models from the point of view of what is the core ideas behind them. And let me try to share with you what I've understood. This is certainly not the end of the story, and it's not meant to be completely technically accurate or the final word on this, but it's my intuition for how these things work. So the way diffusion models work is, you've got some distribution from which you're sampling real images, and then you slowly, gradually add noise to them, and you end up with a sample which is basically all noise. Okay, the signal is essentially disappeared. That part is easy. This is the modeling part. You can take an image from a real image and associate it with a sample of noise. What we're more interested in is to start with a sample of noise and go the other way. In other words, you start with a sample of noise and you want to sample an image from the distribution P of X. How do you do that? It seems like magic. And one thing from my background is image restoration, okay? So one thing that we realized immediately was that what people call generative modeling, which is you start with noise and you generate an image, is sort of an extreme version of what we've been doing for decades, right? Which is image restoration. And so we wanted to put these things into the perspective where it sort of made sense to us a bit more. All right, so let's see how we might do this. Remember, the idea is that we want to start with a sample, start with something, with some initial condition, and march towards P of X, okay? One way to do that is to define what's the so-called probability flow. If you look at the right-hand side, this is basically an ordinary differential equation. And the right-hand side allows you, it's a flow in the direction of the probability density from which you want to sample. Okay, well, it's nice. And again, this is just one way to do it. That's great. By the way, for all of you who are signal processing people, this is not the score function you're thinking. They have changed the definition of score function on us. The Fisher score function is when you take the derivative with respect to parameters of a distribution. They take the derivative here with respect to X. So please keep that in mind. All right, so this equation, again, this is fine, except that you don't know how to compute the right-hand side. So you can't really solve this equation. But it turns out Tweedy's formula, again, comes to the rescue. So remember this equation. MMSE estimate, you can write it as X plus T squared gradient of log of P. And I can rewrite this. And if I rewrite this, you can see that the right-hand side of the probability flow equation, I can write it now as the residual of the MMSE denoising. Okay? Does that make sense? Okay, so this is the first step. So this is the residual flow now. I've got dx dt equals xt minus this MMSE denoiser. Okay, one more step is required. I don't have an MMSE denoiser, right? Very, very hard to compute. So the next step that we do is we replace the MMSE denoiser with our favorite denoiser. And now we have an ordinary differential equation that we can solve with all kinds of various numerical techniques. Okay? This is the guts, if you like, of diffusion models. And the choice of the denoiser makes all the difference. So now, if we want to think about this in practical terms, how do we do this? Well, you have training data that gives you an empirical prior. You have a denoising residual that approximates the MMSE, and you get the score function, and then you have a PDE, and now you solve that PDE with some numerical. You have this ODE with some numerical technique. That's the essence of these ideas. So we wrote a paper that kind of explains things in these terms, and if you're interested in reading more about it, I would love to get your feedback on this. This was published, I think, in June in Transactions on Machine Learning. It describes not just generative modeling, but inverse problems in these terms. And you can think of it as an implicit diffusion process. There's no analytical degradation. For those of you who solve inverse problems, we don't have a forward model. All we have are paired data, clean data and degraded data, whether it's noise or blur or any number of things. And it's competitive on various restoration tasks, but it turns out as a side effect, it's also got generative capabilities. And you can just generate images from noise as well. Okay, so I'm going to tell you a little bit about the details of this method. A typical inverse problem is many to one in the sense that many clean images could have led to the degraded observation that you have, right? This is, ill-posedness 101. When you solve inverse problems, you often get this behavior that's called regression to the mean, and I'll put it more generally, regression to an aggregate solution, because what you're computing is somehow an aggregate of all possible solutions with some penalty attached to it. And so if you try to solve an inverse problem in one big step, it turns out the likelihood of suffering from this regression to the mean or regression from the aggregate is much higher, and you get lower quality results. But what we do is we try to break this process down, and this is basically diffusion, into small steps that split the large problem into tiny pieces. And instead of going directly from input to output, we do it in tiny bits. And this is, imagine solving a problem where you have a little bit of blur that you want to deblur versus solving a problem where you have a lot of blur. And so what we're doing here is we're taking a blurry image and deblurring it a little bit, and then deblurring it a little bit more, and a little bit more, and so on and so forth. And this turns out to be basically diffusion. The heart of this approach is this proposition, which is really trivial to show. And what it does, it shows you that you can propagate the MMSE estimate. In other words, if you wanted to compute the MMSE estimate of x at some time s given t, you can do that by doing a linear combination of MMSE estimate of x0 given time t with xt. And this allows us to think about the solution as not going all the way forward, but kind of thinking about it as a linear combination of a small estimate, of a small time estimate of the solution with the original image that you had, and then continually refining that as you go. And so this ends up being basically the equation, which is very, very simple. It's an iterative procedure that computes this MMSE estimate, which I guess you might be thinking by now, we don't have that MMSE estimate, and you'd be right. And so what we do is, this is still unknown, right? And so we replace this with a neural network, not just one, but you need to train these neural networks for a sequence of t values. Okay, so you need a network trained for a little bit of noise and one for a slightly larger amount of noise, and so on and so forth. If you can get one network that does all of that, generalizes across a large number of noise values, that's great too. So here's an example of kind of how this is different than what you would do with an ordinary estimate. This is just denoising locations or positions of samples. So the actual manifold is only those 4 orange points, okay? The blue are sort of your scattered data. And when you run this diffusion forward, if you just do direct regression, you end up with the red points. But if you do this approach where you increment slowly, the points end up only on the manifold where they're supposed to be. This is just a toy example, if you like. And so we can apply this to many, many different things, including super resolution, noise reduction, deblurring, you name it. So when it says one step, that's, what I said, you just try to go all the way to your final solution. You get this kind of blurry looking thing. And if you do it in 500 steps, you get something much more compelling. This is another one, JPEG artifact removal. You start with a very low quality JPEG image. And after 20 steps, you can recover things like fur and bits of plants and so on and so forth. Okay, and then the last part of what I want to share with you is denoising or denoisers as implicit regularizers or priors. This is work that we did a number of years ago, almost 10 years ago now, with Mickey Elad and Yaniv Romano, called regularization by denoising. It's been used in many, many different places now, and it's still fairly popular. But let me take you back a little bit to the history of how the imaging community kind of came to think about these ideas. To use denoisers as regularizers or priors, there were kind of two major works that developed in this direction. One was by our colleagues at Purdue, who came up with the so-called plug-and-play priors for model-based reconstruction. The idea there was that you would write down your loss function, you would solve your optimization problem using ADMM, and in the process of solving using ADMM, one step stood out as basically being a denoiser. And so our colleagues very cleverly suggested, why use any particular denoiser? Let's just use whatever denoiser we want in there, and hence the term plug and play. And that was kind of a revolutionary idea. And a lot of people started playing with it, and it's very successful, and it still is. In 2000, so that was in 2013. In 2017, maybe a year before that, we started thinking, okay, well, can we do something that's a little bit more principled as opposed to just replacing the denoiser with something arbitrary? Maybe there's some loss function that we can optimize. And so that was the idea behind regularization by denoising. By the way, to give you the punchline, it turns out that no matter which of these operators, which of these approaches you use, the bottom line is you get something very similar to the diffusion approach. You basically apply a linear operator, then you apply a denoiser, and you apply another linear operator, you apply a denoiser. So they all kind of have the very similar computational structure. Okay, so how did we get to regularization by denoising? So the history around this is that folks were using this term here, X transpose LX, as a regularizer for quite some time, all the way back to 2008, Koifman and company and so on. The L that they were using was basically this identity minus WX that I mentioned to you before. Okay, so this kind of pseudo-linear form. This has a couple of problems. One of them is that the Laplacian matrix is actually hard to compute because it's huge. And the second thing is that working with X is cumbersome because it depends on X, but you can circumvent that by, like I said, you can fix X, compute W, and then update in the next iteration. But what we did is we just took this one step further, very cavalierly, and we said, well, why, that loss, the Laplacian regularization is like X transpose X minus W times X. So why stick with WX? Why not just replace that with a denoiser? Okay, so it's now X transpose X minus F of X for an arbitrary denoiser. Well, you still have to compute the gradient of that R, right? And it's not easy to compute unless F satisfies particular properties. And it turns out on the right regularity conditions, if the Jacobian of F is symmetric and you have a certain homogeneity property. So remember, I mentioned the Jacobian being symmetric earlier. So that comes back and it's relevant again here. If those conditions are satisfied, then it turns out the gradient of that R is magically just the residual. And so we started applying this to inverse problems fairly successfully. So as I said, under these conditions, you have very easy access to the gradient of the objective. The objective, you can show that the objective is convex if F satisfies these properties and it's contractive. And now you can leverage very powerful optimization algorithms. But even more importantly, it turns out that if the properties that I just mentioned to you are not satisfied, this approach somehow magically still works. And there's been a bunch of work that has been done over the years, and many, many papers have written trying to understand why that is. And that's kind of interesting as well. In many ways, the same thing is true for diffusion models. Remember I said, you get this nice ODE, if the right-hand side via Tweedy's theorem is exactly the MMSE residual, well, people just replace it and stuff still works. Okay, and this, pardon me? No, it almost always works. It's kind of amazing. Okay, so I'm going to show you a not very sophisticated numerical method. I said you can use powerful numerical methods, but this is about the dumbest numerical method you can use, the fixed point iteration. And so if you look at how the fixed point iteration works here, to update x, you get this first term, which is just fixed. You can compute it once. You don't have to compute it again. You can think of it as a bias. H transpose H plus lambda I inverse is a linear filter. It's just a convolution. And then f of x is just a denoiser. I can just slightly rename things and call f of xk zk. And then what you'll see is that the iteration just looks like this. You take zk, you apply a linear filter to it, you add bias, then you apply this f, which is a nonlinearity. Okay, so this looks very similar to one step of a convolutional neural network, right? You take the input, you apply convolution, bias, nonlinearity. Except that the nonlinearity here, remember, is not a scalar nonlinearity. This is a full vector nonlinearity, f, which is a denoiser. But again, from a very broad point of view, you've got a linear operator, denoiser, linear operator, denoiser, kind of a very similar path, if you like. And this is an example which, you know, it's kind of bizarre if you think about it. You start with your image, you blur it, and then the output on the right-hand side is using a median filter, which demonstrably violates the conditions that I set out for you, and it still works. But also, it's a little bit like a magic trick. If you told somebody I can do deblurring with a median filter, they'd say, well, were you nuts? But it seems to work. Okay, so I will wrap it up by giving you some conclusions. So denoisers, I hope I've managed to convince you that denoisers, after many, many years of kind of being these workhorses in the background, are now recognized across many different fields of work as fundamental building blocks for imaging, for machine learning, for computer vision. Their form is that they're basically stable perturbations of identity. That's one really useful takeaway in terms of what we're doing. The generality is really important. They can solve lots of different inverse problems. It's like a Swiss Army knife. You can pull out and solve lots of different problems with it. And in terms of modeling, the giveaway, the insight that I want you to take away is that having a good denoiser is like peering into the nature of natural images. The denoiser has learned something about the statistics of natural images because it's able to reproduce them in with a high fidelity, in a high fidelity way. And with that, I will thank you very much and stop here.